Alright, welcome back. Today we did a lab where we tried to figure out how waves interact by dropping water into a tank and observing how it ripples out with different obstacles. And today I want to go over some things about waves and just make sure we understand the different parts of waves and how they interact. So we've already been over this vocabulary before with filling out our foldable, but I just want to review it again. We talked about amplitude a little bit today when we discussed interference, when waves come together and they either cancel each other out or they add on to each other's height. That height is also known as amplitude. And the official definition is that it's the greatest distance that the atoms of a medium would move away from their original resting position as a wave passes through them. And so we have to remember that waves are that the matter is constantly in a state of vibrating, but it's typically vibrating in a certain place or in a certain location. So when a wave passes through them, it moves them away from their original spot until they can kind of settle again. Wavelength is the distance between the crest of one wave and the crest of the next, or if you wanted to point out the trough of a wave and match it up to the next trough, basically any two matching or corresponding parts of a wave would give us our wavelength. Now I've said crest and trough, just to review that. The crest is the highest part of a wave and the trough is the lowest part of a wave. And in terms of the word transverse, the pictures of waves that we have on our notes today, it's like the little squiggly line. That is what a transverse wave would look like. It would be kind of similar to if we had a rope and I held one end and you held the other end. We pulled it tight and one of us flicks the rope quickly. You would be able to see a wave pass from one person to another. So that's what a transverse wave is. So if we could label the parts of the wave, right here would be the trough. And the top part would be the crest. And from one section to another would be wavelength. And this line here represents the resting or original position. So from this line to the crest would be amplitude. So comparing these two different waves here, if the wave looks like it's squished together, that means that the crests are closer together. That means we have a shorter wavelength. The length of the wave is shorter. When the wave is spread out more, that gives us a longer wavelength. And we talked about speed last 9 weeks and how it is the amount of distance that an object can travel in a certain amount of time. So when we apply it to waves, it would be how far a certain wave could travel in a specific amount of time. So we haven't really talked about the word frequency yet. And I like to compare this to busy stoplights that you may have experienced if you've been in Lynchburg or another city before. A lot of times there are some areas that have lots of traffic. And so if you're sitting at a stoplight and you have a lot of cars sitting there and the light turns from red to green, if the cars try to sit closer together, you can typically get more cars through that stoplight. If the cars spread themselves out a whole lot, you're not going to get as many of them through that light until it turns red again. So in terms of waves, the frequency would be how many complete waves would pass through a given point in a certain amount of time. So you can think of the waves themselves as the amount of cars that are trying to get through that intersection. So the shorter the wavelength and the more smushed together the waves are, the higher the frequency is. The more spread out the waves are, the lower the frequency would be. So we have a formula, and again we've got the triangle to help us remember the relationship within this formula. So we've abbreviated speed with an S before. For wavelength, we've dealt with work, we've had weight, we've had watts as our unit, and all those things have been abbreviated with a W. And sometimes in math and in science, instead of using a letter from our English alphabet, we'll take letters from the Greek alphabet and use them to abbreviate when we're putting a formula together. So for wavelength, instead of using a W, there's something called lambda. And this looks kind of like if you're looking at a slide from the side from a profile. It kind of reminds me of the stairs going up and then the slide going down. Or if you've ever, we talked about Pi Day the other day. It's like pi, but taking away one of the legs so everything kind of falls down. So this letter is called lambda, and this is what we'll use to abbreviate. And then we have frequency, and we'll still use an F for that one. So let's put it into the triangle. Whatever we put down here, remember we have those two blocks of the triangle are multiplied together. So we'll have the lambda or the wavelength here, and then frequency filling out the bottom. Speed will be at the top. And just to remember the units we use meters per second typically with speed. For wavelength, this is just another type of length unit, so this will be in meters. Now frequency, we said, is going to be how many we can get for every second, like how many waves pass through per second or per minute per any given unit of time. And so 1 over a second is equal to something called hertz. And we abbreviate that with an H and a Z. So the reason it's capitalized is because it's named after the person that did a lot of studies and a lot of experiments dealing with trying to figure out how waves work. So let's practice using this formula. We've got the speed of a wave on a rope is 50 centimeters per second. Okay, so we got centimeters here, and its wavelength is 10 centimeters. We want to know the frequency. So we know that from the triangle, frequency is speed divided by wavelength. So it says the speed is 50, and then the wavelength is 10. You don't need a calculator for that. 50 divided by 10 is 5, and then we're going to use the unit hertz, which again is Hz. Two other practice problems. A wave has a wavelength of 5 millimeters and has a frequency of 2 hertz. We want to know speed this time. Speed is wavelength times frequency. So this time the wavelength is 5 millimeters. The frequency is 2 hertz. 5 times 2 is 10. And we know that the length part of the speed unit will be in millimeters this time. And hertz always deals with seconds. So 10 millimeters per second. Finally, we know the speed of a wave on a guitar string is 100 meters per second, and the frequency is 1,000 hertz. And we want to know wavelength. Wavelength is speed divided by frequency. And my speed is 100, and my frequency is 1,000. So it's kind of like if we could get rid of the zeros that cancel each other out, that would be the same thing as 1/10, and we can change that into a decimal, which is 0.1. And because it's wavelength, we need to look at the length part of our speed unit, which is meters. So 1/10 of a meter would be your wavelength. We're going to do a lot of practice of this in class on Monday, so if you have any questions, just make note of it and we'll talk about it, and we'll get lots of practice together, working together and talking about it, and you can have a chance to talk to me about it too. So be ready, and I'm looking forward to applying this to sound next week. Have a good weekend.